All right, we are back at AP Review. This is 2015 AB BC for response 4. Consider the differential equation dy dx equals 2x minus y. Pause. First thing to notice, this is non-separable. The x's and y's are added together and there's nothing you can factor out to change that into some kind of multiplication or division. So you cannot possibly be asked to solve this diffie q. They can ask you to do a bunch of other stuff. They can ask you to derive it. They can ask you to check if a given solution is a solution. They can ask you to do lots of other things, but they cannot make you integrate this to solve. Cool, moving on. On the axes provided, which I drew terribly, sketch a slope field for the differential equation at these 6 points indicated, which are 1, 2, 3, 4, 5, 6. Cool. So a couple things remember about slope fields. They don't care how much work you show. They just want the right slope field. So I'm going to list the 6 points because I think it's a good way to kind of keep all your ducks in a row, right? So it's only 6 points. It's pretty easy to list them, right? So I have an x and a y, and I have my slope, which is 2x minus y, right? That's my slope. So m equals. Cool. So my x points, I always start with the bottom left and work my way up and then to the next column. I don't know why. So negative, my bad, 0, negative 1. Come on, brain. 0, negative 1, right? 0, 1, 0, 2, 1, negative 1, 1, 1, 1, 2, right? So now I'm going to go ahead and plug in the slopes to 2x minus y. You notice in all of these, the x coordinate is 0, so really it's just the negative of the y coordinate. So that'll be a 1, a negative 1, and a negative 2, right? 2x minus y here, the x's are all 1s, so it's going to be 2 minus the y coordinate, right? So 2 minus a negative 1 would be a 3, right? 2 minus a 1 would be a 1, right? And 2 minus a 2 would be a 0, right? So when the AP gives you credit, they're usually looking specifically for any odd, not odd as in the odd number, but odd as in unusual kinds of slopes. So flat slopes, like when you have a slope of 0 or an undefined slope, that's the first thing they're going to look for. So I should have a flat little snippet of slope right there, right? So that should be horizontal, and then I'll find all the other ones, but I would point out that getting the easy or unusual kind of slopes done first is kind of valuable. So here I should have a slope of up 1, right 1, which means my slope looks kind of like that. Right here, I should have a slope of down 1, right 1, which means my slope looks kind of like that. And here I should have a slope of down 2, right 1, which means I'm pointing actually to the exact same spot right here again. Here, I should have a slope of positive 3, which is 1, 2, 3 up, and then over, so that's pretty steep going up. This one should be a slope of 1, so that's up 1, right 1. And then I have my slope of 0, which I already drew. So that's my slope field, right? It's probably worth 2 points. If they ask you to sketch a solution curve, sometimes it's worth an additional point, but here they did not. All right, part B. Find d squared y dx squared in terms of x and y. Then they ask you to determine the concavity of all solutions for the given diffie q in quadrant 2, give a reason. Okay, so we don't need this guy right now, right? So let's go ahead and do part B, right? We're going to find d squared y dx squared, right? So that's going to be the derivative of the 2x, which is a 2, because you're deriving x with respect to x, minus the derivative of the y, which is going to be a dy dx. But that's not in terms of x and y, because dy dx is not an x and a y unless I replace it with this. So I'm going to get a 2 minus the quantity 2x minus y. So that answer is fine. If you want to distribute the negative, that's great. If you don't, that's also great. This is fine, okay? Again, if you want, you could also make this a 2 minus a 2x plus a y. Also fine, okay. Now, that's the first thing they asked me to do. But then they asked me to, well, they don't say use that, but it is sort of implied since we're talking about concavity. So then they ask me about quadrant 2, right? So what I want you to think about is that quadrant 2 is where the x values are negative and the y values are positive, right? So x is negative and y's are positive, right? That's this quadrant right here, right? Negative x, positive y. So they ask you to determine the concavity of this problem, or of this curve in that entire quadrant, right? So what I want to point out is if your d squared y dx squared is a 2 minus a 2x plus a y, right? So if you think about this in terms of negatives and positives, x is a negative number. So you have a negative 2 times a negative number, meaning that this is going to be 2 plus a positive number in the end, because you're negative 2 times a negative number, and then y is also a positive number, right? So essentially what's going to happen is you're going to get a 2 plus a number that's going to be positive, because it would be a negative times a negative, which would be positive, plus another positive number. So this thing has to be greater than 0 in quadrant 2. Well, if d squared y dx squared is greater than 0 in quadrant 2, then what that means is that the curve is concave up. All right, so what they needed you to recognize is that concavity is about the sign of the second derivative, right? And because this second derivative could never be smaller than a 2, because it's a 2 plus essentially two positive numbers here, because of that, this curve has to be concave up in quadrant 2. Cool. Part C. Let y equals f of x be the particular solution to this differential equation with the initial condition f of 2 equals 3. Now, before you think, hey, they're going to ask me to solve, remember, this is non-separable. You cannot solve this. So they can ask you to do stuff with this information, but they can't ask you to integrate to solve. All right. Does f have a relative minimum, maximum, or neither at 2? So remember, you have a first derivative and you have a second derivative. So I'm going to give myself a little bit of space, right? So for the curve y equals f of x, you have a first derivative, right? You know that dy dx is 2x minus y, and you also have a second derivative. You know that d squared y dx squared is a 2 minus a 2x plus a y, right? So remember that we know a test that uses the first and second derivative evaluated at specific points to find extrema. Right? The second derivative test says that if y prime is 0 and y double prime is less than 0, then you are concave down but level at a point. That's a max, right? So if at, let's say, x equals a, right? But if y prime was 0 and y double prime were greater than 0, then your function must be concave up and flat, and you must have a min, right? So that's what they're asking you to do here. They're asking you to evaluate both the first and second derivatives, right? The first and second derivative that we have, because we were given the first derivative and we found the second derivative. We're going to evaluate those at the point 2, 3 and see if they come out positive or negative. So, and then depending on which one happens, I'll know which of these two is my answer. Now, there is the possibility that it's neither, right? But that's pretty rare. They usually give you a pretty cut and dry answer here. It does happen, right? The neither is going to happen, right? So usually it's one of these two. The neither is going to happen if y prime doesn't equal 0. Because see how this has to happen first? You have to be level first. So if that happens, there's no point in even checking the second derivative. There is another case, but this won't happen here. If y prime is 0 and y double prime is also 0, that's not a neither. That's what we call inconclusive, meaning you need a different test. So you need a different test, okay? So it's likely, I would say, probably about 70% of the time it's one of these two, and the other, maybe more than that, probably 80% of the time it's one of these two, and the other 20% it's neither. It's really never the inconclusive thing in this situation, because if they're setting you up to use the second derivative test, they want the second derivative test to apply. The second derivative test only applies if it's these situations. So really, I'd say this is probably about 80% of the time, and this is probably about 20% of the time. And this is really pretty much 0% of the time on the AP, because again, they're setting you up to use the second derivative test. Again, it might be like 0.001% of the time it might happen. So let's finish this out and see what situation we're looking at. If I try dy dx, evaluated at the point 2, 3, when I plug in, I'm going to get 2 times 2 minus a 3. Well, that's really interesting, because what I end up getting is 4 minus 3, which is 1, and 1's not 0. So despite the fact that I told you that most of the time it's one of these cases, the answer is neither. And the reason it's neither is because the first derivative evaluated at that point is not 0, and you can't have an extrema there if your first derivative is not 0 or does not exist. So the answer is neither. Part D. Find the values of constants m and b for which y equals mx plus b is a solution to the differential equation. Okay, so here's the idea for D. And this is a little bit thinking outside the box. It's a slightly hard problem. So let's say we know that the solution, one of the solutions is y equals mx plus b, right? We also know that that means that dy dx, right, would just be m. Like if you derive this, dy dx is just m, right? So here's what I know. I know that dy dx was supposed to be this, but in this, if this problem is the solution, which they're saying it is, then dy dx is m. So what I can infer from that is, oh, 2x minus y has to be m. Right? Is that okay so far? Okay, so there's a couple different ways to do this, right? I'm going to make the argument that I know what y is, right? Y is mx plus b, right? Because they're saying that's the solution to this thing. So I could plug in an mx plus b here and say 2x minus the quantity mx plus b has to be m. And there's another way to do this, and I'll walk you through that in a sec too. If you clean this up and distribute a little bit, you're going to get a 2x minus an mx, right? Minus a b has to equal an m. So the thing about this is if you have an equation, right? If you have an equation like this that is equal all the time no matter what these values are, because m and b are numbers and x is a variable, right? The number of x's, right? So since this is true, this is supposed to be true for all x, right? So for all x, this is supposed to be true. What that means is that the x terms on this side have to equal the x terms on the other side. Well, on the left-hand side, the x terms are 2 minus m, right? Because it would be 2 minus m times this x, right? And on the right-hand side, there are no x's. Well, that must mean that the quantity 2 minus m equals 0, so m must be 2, right? The same has to be true about the numbers. Again, this is an equation that's true for all x, so I'm not solving for x because it has to be true for every x ever. That's what a solution to a diffie-q means. It's true for all x. So the constants on the left-hand side have to equal the constants on the right-hand side. Well, negative b equals m. Since I know that m is 2, that means negative b equals 2. B must be a negative 2. So you get m is 2 and b is negative 2. And that's one totally acceptable way to solve this. So that's one option. The other option that I believe I did previously, which is the same basic gist but looks a little bit different, right? So that was the way the AP guidelines went. So I was able to infer, I went to the same spot where I said, hey, I said this dy dx equals this dy dx, so 2x minus y has to equal m. And I solved this guy for y, right? So I solved for y by adding him over and subtracting the m over. So I got 2x minus m has to be y. But that's the same y as mx plus b, right? So I already know y equals mx plus b. So 2x minus m has to equal mx plus b. Well, the x terms have to be equal. So 2 has to equal m, right? And the coefficient term, or the constant terms rather, have to be equal. So negative m equals b, and since m was 2, negative 2 is your b, and you get the same answer. So there's a couple different ways to get that, but again, you weren't being asked to solve. You were being handed a solution. You were told, hey, this is a solution. Check and see how you can find what m and b are. That's the idea.